When we look at the incredible progress of humanity, the hidden history of innovation isn't just about massive machines or digital microchips. Often, it's about mastering the tiny, completely unseen molecular structures right in front of us. Welcome to this explainer, where we're going to peel back the layers of reality on the everyday powders and crystals sitting right there in your home. We are uncovering the extraordinary science of everyday stuff that is literally hiding in plain sight. So let's dive right in by challenging a pretty huge assumption. When you hear the word salt, I bet your mind immediately goes to the dinner table, right? You picture sodium chloride, that deliciously salty white crystal you sprinkle on your French fries. But here's the thing. In the world of chemistry, that everyday condiment is just one tiny resident in a massive, sprawling metropolis of compounds. Salt isn't just one thing. It's an entire, massive classification of chemicals. To really get this, we need to look at how chemists actually organize the world. A salt family is a broad grouping of chemical compounds that all share a common negative ion. We call that an anion. And because they share this fundamental structural piece, all the salts within a single family exhibit incredibly similar, super predictable chemical behaviors. It's kind of like a genetic trait passed down through a family tree. Once you know the family name, you can reliably predict exactly how that salt is going to act out in the real world. We can actually categorize these compounds into 4 main families based on those anions. For instance, you've got the sulfates with their SO4 2- ion, which gives us things like gypsum. Then you have the chlorides containing the Cl- ion. And yeah, that includes our famous table salt. Next up are the nitrates, like chili saltpeter, and finally the carbonates, like washing soda. By mapping them out like this, all that overwhelming complexity of chemistry suddenly resolves into a beautifully organized, totally understandable set of patterns, which brings us to Section 1, how salts are formed, the neutralization reaction. The creation of a salt is just this beautifully elegant, wonderfully predictable event. It happens through a process called neutralization, playing out in 4 distinct stages. First off, an acid ionizes, basically breaking apart in a solution. Second, a base does the exact same thing. Then, in the third step, these highly reactive ions find each other and totally neutralize their opposing charges. Finally, the dust settles and boom, a brand new salt is formed, usually just leaving water behind as a harmless byproduct. Seeing this theoretical process in practical action really reveals something incredible. Think about the recipe for a sulfate salt. If you take sulfuric acid, which is this incredibly powerful, frankly corrosive substance, and combine it with potassium hydroxide, a super strong base, they do that neutralization dance. And what's left over? Potassium sulfate and water. 2 intense, dangerous chemicals perfectly balance each other out to create a stable, highly useful salt. It feels like chemical magic, but really it's just pure, predictable science. Moving right along to Section 2, powering modern industry, chemicals from common salts. Let's actually jump back to our old friend, common table salt, sodium chloride. Through an industrial process, we can literally split that common salt apart. And when we do, we don't just get one useful thing out of it. We extract 3 highly valuable, equally important co-products: chlorine gas, hydrogen gas, and sodium hydroxide. This trifecta right here is what makes the entire chemical processing industry so incredibly economical. You take one cheap raw material and you extract 3 absolute industrial powerhouses. And this is exactly where that hidden history of innovation really shines. Just look at what these derivatives actually do in the real world. Chlorine gas is out there actively purifying the water you drink and forming the PVC pipes that carry it to your house. Hydrogen gas is a total marvel of modern innovation, used in futuristic fuel cells and synthesizing the ammonia fertilizers that literally feed billions of people. And sodium hydroxide? Well, that's the heavy lifter in the paper industry and a crucial ingredient in the soap you use to wash up every morning. All of this incredible modern convenience traces its roots right back to common salt. All right, Section 3, everyday wonder chemicals, the soda siblings. The crazy thing is, you don't even have to look at a massive industrial plant to find this chemistry at work. Take 2 incredibly common household items: baking soda, which is sodium hydrogen carbonate, and washing soda, which is sodium carbonate decahydrate. I mean, they sound almost identical, right? But a tiny shift in their chemical makeup dictates wildly different uses. Baking soda is a mild alkaline. It acts as an antacid for an upset stomach, and because it undergoes thermal decomposition to release CO2, it's the exact reason your cakes and breads rise in the oven. Washing soda, on the flip side, is the heavy-duty sibling. It has extra water molecules structurally attached to it, which makes it absolutely perfect for removing tough laundry stains, and acts as an essential component in glass and paper manufacturing. Same exact family, completely different jobs. which perfectly sets up Section 4, the hidden water mystery, water of crystallization. Speaking of those extra water molecules attached to washing soda, I want you to think about something for a second. When you hold a salt crystal in your hand, maybe just a grain of sea salt or a pinch of washing powder, it feels completely dry, doesn't it? It pours like sand. It acts totally solid. But is it truly devoid of water? Well, the surprising answer is absolutely not. In chemistry, appearance doesn't always match reality. If we look much closer, we realize that many seemingly bone-dry crystals are actually secretly hoarding water molecules right inside their solid structures. We call this fascinating phenomenon the water of crystallization. And listen, this isn't just surface moisture. It's not like a wet sponge that you can just squeeze out. This water is chemically bonded. It's locked tightly into the physical lattice of the crystal itself. It's structurally integral. In a lot of cases, these hidden water molecules are exactly what gives the crystal its unique geometric shape, and sometimes even its vibrant colors. If you were to drive that water out with intense heat, the crystal might completely collapse into a formless powder or even change color entirely. And that brings us to Section 5, Plaster of Paris, a historic chemical marvel. To truly appreciate how humanity has harnessed this hidden water concept to drive real innovation throughout history, look no further than Plaster of Paris. Now, it takes its name from historical gypsum mining that happened in the Montmartre district of Paris centuries ago. But what makes it a genuine chemical marvel is this incredibly bizarre quirk in its crystal structure. Its chemical formula notes a half water molecule. Now, wait a minute, you can't split a water molecule without fundamentally changing what it is, right? So what does this actually mean? Well, it means that in the crystal lattice of Plaster of Paris, two separate calcium sulfate units are structurally sharing a single water molecule between them. It is quite literally a masterpiece of molecular architecture. And throughout history, humanity figured out how to brilliantly exploit this structure. The process is simple, but absolute genius. First, you take natural gypsum rock and heat it to precisely 373 Kelvin. This exact temperature drives out just enough of that bonded water to turn it into a dry, workable plaster powder. And the setting mechanism? It's just the reverse. When a doctor or an artist wants to use it, they simply add water back in. The powder rapidly reabsorbs the water, completely reforms those crystal bonds, and hardens right back into solid gypsum. This single, highly predictable, reversible chemical transformation is an extraordinary historical innovation. I mean, it gave us medical casts for broken bones, the walls of our modern homes, and some of the most timeless artistic sculptures in the world. So as we wrap up this explainer, I want to leave you with this. The next time you look at a simple white powder sitting on your kitchen counter, or a hardened medical cast, or even just stare at the drywall in your own bedroom, I want you to remember the invisible, intricate molecular architecture that is making it all possible. Chemistry isn't just something that happens in a sterile lab. It is the very fabric of your daily life. And honestly, it really begs the question, what other hidden scientific wonders are secretly powering the objects you touch every single day, just waiting for you to look a little closer? Keep questioning, keep learning, and thank you so much for joining me to uncover the hidden science of everyday stuff.